So review packet for unit 3. Similar to all the other review packets, it's going to give you a sneak peek as to what you can expect to see on the test tomorrow. Some of these questions, I would say the first page is probably my least favorite, just because it really kind of pushes the bounds beyond our understanding of what systems tell us. I'm going to show you some tricks though on how to work these out, and it's probably the page that's worth the fewest number of points overall on the test. So don't panic too much. You do all have the skills though to work through these problems that I'm about to show you. So the first one here, the question is, which ordered pair below is a solution to the inequality y is greater than 2x minus 4? Now, typically, if we were solving this one, we would ideally like to graph it, look for the shaded region, and if those points are in the shaded region, we'd say, yep, it's a solution. But you'll notice very quickly, one thing I did not provide is a coordinate plane. So graphing is kind of not the most practical method here, but that's okay, because if we think about what ordered pairs are, they give us an x coordinate and a y coordinate. So if we look at the inequality, we'll notice that there is a position for both the x and the y. And if we think about inequalities, they're just comparison statements anyways. So what we're going to do, this is where it gets kind of tedious again, is one at a time, plug in these ordered pairs to see what we end up with when we replace both the x and the y. So I'm going to have 4 sets of work here. First one is going to be for the ordered pair 4, 1. And I'm going to use the 4 to replace the x, the 1 to replace the y, and the inequality we're given. And that's going to leave me with 1 is greater than 2 times 4 minus 4. Well, there's not a whole lot to do on the left. Put my little guideline in here. But there are some things I can clean up on the right. So 1's hanging out. On the right, we have a multiplication and a subtraction. Follow our order of operations. We do the 2 times 4. Gives me 8. And 8 minus 4 is going to give me 4. So what I'm left with is a statement that reads 1 is greater than 4. True or false? False. False. So guess what? That ordered pair is not a solution. It resulted in a false statement, so I can cross A off my list. Now, fingers crossed, the solution is earlier on. Otherwise, if it's answer D, we're going to have 4 sets of work. Hint, hint, that may happen on this one. Not on the test tomorrow, though. I don't think I was that mean. So that would just repeat the process. Our second ordered pair is 0, negative 5. Plugging it into the inequality, I'll have negative 5 is greater than 2 times 0 minus 4. You're going to notice this feels really repetitive because we're essentially doing similar steps each time. So the negative 5 stays the same. Greater than 2 times 0, which gives me 0. Bring down the minus 4. 0 minus 4 gives me a negative 4. And what I'm left with is a comparison statement that says that negative 5 is greater than negative 4. Is that true? No. So I threw in a negative comparison there just to kind of be sneaky. Negative numbers do work backwards than what we think. So this one is in fact also a false statement, which means that ordered pair is also eliminated, not a solution. And then we start over. So again, not the most exciting example. So our next one is 2, 0. So plugging it in, I'll have 0 is greater than 2 times 2 minus 4. Run through our steps here. 0 is greater than 2 times 2, which is 4. And 4 minus 4 gives me 0. And I'm left with the statement 0 is greater than 0. Is that true? Yeah?
No.
No. So 0 is equal to 0. And had this been a greater than or equal to sign, we'd be good. Unfortunately, though, 0 is not greater than 0. So even though it seems so close, it is still considered a false statement. So it should be D, because that's obviously the last one left. But let's check. Let's not assume, because when I first started teaching and I was writing my own tests, silly me, now I just borrow from other teachers, I would make mistakes, and sometimes I'd have multiple choice questions that none of the answers were right. It's not the case here, but for the sake of practice, let's check that ordered pair 1, 1. Again, using the same inequality, we're going to have 1 is greater than 2 times 1 minus 4. Cleaning it up here, we get 1 is greater than 2 times 1, which is 2. Bring down the minus 4. 2 take away 4 is going to give me a negative 2. Is 1 greater than negative 2? I'm seeing some head nods. Yes. In fact, all positive numbers are greater than all negative numbers. So finally, took us a minute, but we got to a true result, which must mean that whatever value we just plugged into that inequality is in fact a solution. So D is in fact our answer. Now, if this was the actual test and you didn't do that last bit of work, but you still came up with the right answer because of process of elimination, I'm not going to be too worried about it. But again, we're practicing today, so extra practice never killed anybody. Now, the second one is kind of a tricky one because technically we could use a similar process as we did from number 1. But the problem is that we can't just agree that it has to work for one of the equations. It would in fact have to work for both. So I would argue, why not just solve it instead of checking to see if every single one of those ordered pairs is a solution? We couldn't really solve the top one because you can't really necessarily solve a linear inequality quite like we do the equations, but with a system of equations, we can. So what I would say is, why not try one of the methods we have covered in the past? So we had graphing, we had substitution, we had elimination. Any idea which one this one's favoring? Why elimination? I would agree with you. Do you know why?
Because you're eliminating numbers to get one by itself.
Well, not necessarily to get y by itself, but we do want to eliminate something. And it's not just the numbers that we're interested in eliminating. We actually want to eliminate one of the two variables. For me, though, if I was looking at this problem, I would say, well, my x terms are lined up, my y terms are lined up, so are my equal signs, so are my constants. That's telling me elimination might be a better choice. I don't have to move anything around, but I do have to make sure that the second condition is true. And for elimination, if you recall back to last week, Wednesday, I think, when we use elimination, not only do we want them to line up, we also need opposite coefficients on either the x's or the y's. Now we're close. Their signs are both opposite on x's and y's, but are they exactly the opposite?
No.
No. Now, remember, multiplication is our only tool to make changes here. So if you think about it, It's good to have a goal in mind. Which variable do you think will be easier to eliminate?
I think that or the negative 6x gives you times the bottom equation by 6. The negative 6x and the positive 6x can apply.
So to summarize, for those, I don't know if it came through very well for those on Zoom. So you're focusing on the x's. And Amy, you're saying that if I multiplied 1x by a 6, it would become a 6x.
Yes.
Now, we have to agree that the whole equation is going to change also, which is fine. But we see here, multiply negative 2y and 3y by each other. Miranda, that would also work. So this is where I mentioned last week that systems of equations are a little bit tricky because there are so many possible routes we could take. So multiplying negative 2 and 3 together on the y's would give you a positive and negative 6y, which would work. If I was lazy, not lazy, if I wanted to cut out a step, it's just being clever, I could multiply just the bottom one. So there are a couple routes here. I'm going to go with Amy's just because she was first to come up with the idea. But Miranda, I challenge you to go the path you're taking. We should reach the same conclusion. So Amy's goal was to get opposite coefficients on the x's. And to do that, she decided that if she multiplied the bottom equation by, was it a positive 6? A positive 6. Let me highlight what it's going to affect. We're really focused on how this is going to change with the 6. Everything else will change, which is why I wrapped it in parentheses, but we're particularly interested in how the x's change in this process. Now, for the sake of room here, I'm going to bring this all the way over here. I'm not changing the top equation, so I'm going to copy it down. Negative 6x minus 2y equals 28. And then the bottom equation, everything's getting multiplied by that positive 6. So we're going to get 6x plus 18y equals, that's what, 120 plus 12 is 132. I'm sorry, 132. And I'm happy now because if I look at those x's, when I go to multiply them together, they will cancel or eliminate. That's why we call it the elimination method.
Back in Central, they use the cancel out method, but it's the same thing, but it's just.
Yeah. So depending where you learn it, there's always different names for it. But yeah, the goal is the same. If we can get one of those variables to disappear, we can solve for one variable. We've been doing that since unit 1. So when you add this negative 6x with the positive 6x, technically it becomes 0x, but 0 anything just disappears. Negative 2y plus 18y is going to give me positive 16y. And 28 plus 132, I believe, will give me 160.
And then the bottom goes by 16.
Yep. So what we're left with is a one-step equation. And to get y by itself, to figure out what it is, all we have to do is divide by that 16. And we end up getting that y equals 10. Now, at this point, usually students point out, being that it's multiple choice, if you look at the options, there only appears to be one that has a y coordinate of 10. And that would be answer D. But again, careful with your assumptions. And because we're practicing anyways, let's make sure that the x we get does in fact turn out to be negative 8. How would I, had this not been multiple choice, how would I have found that x?
By taking the y and plugging it in for the y with the negative 6x minus 2y with equals 28. But
Okay.
instead of having the 2y, you would put the 10.
Okay. Yes, let me quickly summarize though. You get on a roll and I hate to interrupt
Yeah, I know.
because you're just ready to crank out that problem. But you're telling me that now that I know that y is 10, I can replace this y with a 10? Quick question, could I technically also replace the other y with a 10?
Yeah, but it would just make sense since you use the bottom equation to can't to get the y by itself. It would make kind of sense to do the top equation other than the bottom.
So what I would suggest in that situation is you use what you feel most comfortable with. So if it makes more sense to you to use the top one, by all means, use the top one. I would argue that since both come out with the same, go with what your gut instinct tells you to. If I was doing it, personally, I'd probably do the bottom one, only because those numbers are a little bit smaller. But to prove to you that it doesn't technically matter, so long as you watch your signs, watch how you replace it, I'm going to go ahead and use the top one. So that was the negative 6x minus 2y is equal to 28. I now know that anywhere I see a y, I can replace it with a positive 10. I can rewrite this equation then to say negative 6x minus 2 times 10 equals 28. And what I'm left with is something that I can now work through and reach a final solution for x. So hopefully the parentheses catch our eye first. So I have negative 6x, negative 2 times 10 gives me a negative 20. And then I just solve it like a two-step equation. I'm going to add 20 to both sides. I'm going to get negative 6x is equal to 48. And then last but not least, I'm going to divide both sides by that negative 6. And I get x equals a negative 8, which is what we suspected. But now we can confirm because the algebra supports that. Don't mind me, my OCD is going to step in real quick. Make it all pretty. But just like that, we found that the y value would be 10. We use that to find the x value as negative 8. Remember that your final solution is an ordered pair, and ordered pairs are always written with the x coordinate followed by the y coordinate. Okay. So first one was a little unorthodox, a little bit different than what we're used to. Second one kind of flew right into what we did last week. I think it was last Wednesday. Last week was such a weird week. Number 3, again, pushing the limits as to wrapping our head around what we've kind of picked up along the way with systems of equations. It's not asking us to actually solve this next one. In fact, it's telling us that the given system of equations has no solution. So if you can't see it there, that system of equations is y equals 1/2 x minus 3 and y equals 1/2 x plus 1. Now, if you wanted to, if you had a graph, you could try graphing them, look at it that way. You could use substitution or elimination, but the fractions are in there. That'll be kind of annoying. But let me ask you though, is there a way we can actually validate that this system is definitely no solution or has no solution?
They have the same slope.
What does that mean?
That they're going to be running next to each other, correct?
Getting close. Yes. I'm looking for a particular word though.
You never intersect.
So both, you actually answered the next two questions. So Lana said that means with the same slope, they are parallel. And then Amy, you said that they never intersect.
Yeah.
So that's kind of a series of events. So they have the same slope, which means they're parallel. Parallel lines never intersect. If there's no intersection point, there's no solution. So really that, I mean, I don't think we can get any more specific than that. So if I was to write this out, I would say they have the same slope. which means they are parallel lines. Let me zoom out here just a little bit. So that's my first sentence. My second one would say that parallel lines never intersect, which means there is no solution. So kind of a little short cause and effect. Same slope means they're parallel. Parallel lines never intersect. No intersection point, no solution. So part B asks to give another example of a system of equations with no solution. So we actually have all sorts of ones that we can do here. Sorry. Let me make sure you guys have time to write that down. But can anyone give me an example of a system of equations that would also have no solution?
Can you do y equals -3?
Y equals -3? We technically could. What would be the second equation? So technically this would work. Y equals -3 would be a horizontal line. So as long as you could give me another horizontal line, say y equals, I don't know, 7. If they're both horizontal, they're parallel, they'll never intersect. That one's a little bit unusual. You could have done something like y equals -3x plus 9 and y equals -3x minus 5. That'd be another example. In fact, that list could go on and on and on. There's infinitely many right answers here. So I'm going to make a little additional comment here that says that answers will vary as long as the slopes are the same. So long as you give me any two equations, linear equations where the slopes are the same, they would be parallel. So like I said, infinitely many possibilities. I've listed 2 there. The most important part though is that the slope is the same. I should probably add though, do you also want the y-intercepts to be the same? What would happen if both the slopes and the y-intercepts were the same?
They'd be on top of each other.
They'd be on top. It'd actually be our secondary special case. And if they're on top of each other forever, how many solutions does that give us? How many points are on a line? Infinitely many. And if the lines are on top of each other, that means they're always intersecting. So we would have infinitely many solutions. So yes, we want the slopes to be the same, but we actually don't want the y-intercepts to be the same, because that would be a different case altogether. Our last example here, or actually it's just a request, and that is to compare and contrast graphing a linear equation and a linear inequality. Use complete sentences, include at least one similarity, one difference. So I'll help you out with this one. First off, we graphed both of them as lines. Is that correct? They both started off with a y-intercept. We used the slope. So I would say they both begin as lines using the y-intercept and slope. So in our notes, when we first kind of were graphing both of these, I pointed out very directly that the first two steps in graphing a linear inequality were the exact same two steps we used to graph a linear equation. We found the y-intercept, we started there, we counted out our rise over run, found additional points, had our line. And we do the exact same thing for linear inequalities. So this would be our similarity. Our difference, what's different between a linear equation and a linear inequality?
An equation has a solution.
An equation technically has, well, lots of solutions because every point along that line is considered a solution. But if I were to graph just an equation and then next to it an inequality, what would be a very visual difference?
I know it, I just don't know how to say it, and I don't know if I'm right.
Go for it. Worst case scenario.
One is equal, one isn't.
One is equal, one isn't. And it's because one of them isn't, we actually do something extra on the inequalities. Do you remember what that was? I found it very soothing myself.
I don't know.
That's okay. So one uses elimination. So if we're thinking in terms of systems, yes, we use elimination for equations, but I'm thinking very, very, very visually. Let me throw it back to so here's an example of graphing equations from a past lesson. Here's an example of graphing an inequality. What's different?
One is shaded.
One has a shaded region, the other does not. Also, we could use a different type of line. Sometimes they were dashed as well. So there we go. So we could say that linear inequalities also include a shaded region. So we didn't necessarily do any shading for equations, but for an inequality, that shaded region gives us even more points to include in our set of solutions. So Marissa, you weren't wrong in the sense that if we're talking about systems specifically, we used elimination for the equations, whereas we didn't use it for inequalities. We used just graphing for inequalities. So that would, I would argue, that would be a sufficient response as well. All right. So first page is probably my least favorite just because it's rather abstract. It's good because it pushes your depth of understanding, but I don't know, I just don't like it. I like getting into the next few pages where we actually get to apply the skills, practice the skills we've been picking up through this short unit. So the next page is all things graphing systems of equations. So a couple things, again, remember reviews, I like to put little notes in the margins. So identify the solution of the system of equations graphed below. Some things I'm going to note here in the margin is that we are looking for the point where the lines intersect. You ever get halfway through a word and forget how to spell it? Second thing I would mention though, real quick, as a reminder, it is easier to graph when the equation is in slope-intercept form. which, quick throwback, y equals mx plus b. So a little bit of information there for us. You know me, I'm going to pretty it up real quick. Zoom out just a little bit. So the first comment really just kind of clarified what it is we're actually looking for. We're looking for the point where they intersect. The second comment there serves mainly as a reminder. We spent the whole last unit graphing a lot. So just a reminder that if we're going to have to graph ourselves, it really helps if they're in slope-intercept form. Now, conveniently for us, this first one, we haven't even been given the system of equations. We've just been given the graph that's already been done for us. So what would be the solution for that system?
3, 3.
Close.
Well, actually,
That's all right. I'm zoomed out a lot. Miranda's got it in the chat. 3, 2. So we're looking for that exact point there. Don't forget though, the x coordinate always comes before the y coordinate. So that one is located at 3, 2. So not really any work to do there other than spot the point where they crossed and then identify that based off of its coordinates. Again, don't hesitate to stop me if you have any questions. You're like, Josh, where'd that come from? Gladly respond. Now, usually, if you're graphing a system of equations, you actually have to do the graphing yourself. So on these next two systems, we have a little bit of work cut out for us. So I'm going to pause for about 30 seconds here and pause the recording as well. That way you guys can jot this down and then we can get to work on them. Okay, so jumping into these next two systems of equations, we're going to solve them by graphing. So we actually need to see the graph first. Yes, I know we could solve them other ways, but really the graph is important to practice here as well. Why do I like this first system? It's already what? Well, they're both linear equations, but they're both in slope-intercept form. So for the sake of my work, you know what? I think I can just get away with splitting this here as such. I'm going to start with the top equation. What is my y-intercept? 3. Yep, positive 3. And what is the slope?
1/2.
Positive 1/2. So if I was to come down here to my coordinate plane, we're going to start at positive 3 on the y-axis. And with a slope of 1/2, I'm going to travel up 1, rise 1, I should say, and run to the right 2 units to get a second point. And if I do it once more, I'll get a third point. And if I'd like a few more points, I could do the exact opposite, go down 1, left 2. Grab my straight edge here. Drawing my line.
Josh, I'm getting frustrated. I don't understand any of this.
Which part? Where did I lose you?
At the beginning.
At the beginning. Well, you told me the y-intercept was 3.
Yes, I understand that part, but it's
What is a
this
y-intercept?
part.
Well, hold
Where
on.
The thing crosses the y-axis.
So-
It's on the y-axis.
So that's why I put my first point right here.
Okay.
The second thing, which I think you also helped me identify, was the slope. is 1/2. So 1/2, just as a reminder, in terms of graphing, we usually think of it as rise over run.
Now I understand. Because I understand the rise of the run.
So that's where I got these additional points. I started from that first point we graphed and I rise. So I went up 1 and I ran, since it's a +2, to the right 2, up 1, right 2. That's where I got the next 2 points. I did the exact opposite. I went down 1, left 2, because if you think about it, down is negative, left is negative, a double negative is still positive. And that gives me all sorts of points to look at. And the reason why, in my opinion, it's so important to get as many points as you can see on your coordinate plane is because if you recall, we are looking for the point where they intersect. So having as many of those clear cut points on the graph itself is going to help us out. Yes, I got it.
Can you go down a bit?
I haven't done anything down there. It's all blank
Oh, sorry.
because I can't have a solution yet because I'm looking where they intersect. And they haven't intersected because I've only graphed 1 line so far. I'm only halfway done. So if I was to look at the second linear equation, what is its y-intercept?
-3.
It's going to be a -3. Yep. And its slope is a +7/2, which seems rather steep, but we'll just make sure we count out carefully. So this one has us starting all the way down at -3 on our y-axis. And with a slope of 7/2, I'm going to rise 1, 2, 3, 4, 5, 6, 7. And then I'm going to run to the right 1, 2. And conveniently for me, that is a point I already graphed, which is good news because that's really the point that I'm looking for. So Miranda's already ahead of me. She already knows what the solution is. The solution is where they intersect. And at this point, they appear to be intersecting at the ordered pair 2, 4. So a little bit of work up front. We had to graph them ourselves. But once we got them graphed, just like the first one, we really just need to pick out the point where they cross or intersect. Okay, so the second one here is a bit of a bummer. Why is that? I have to solve each of those for y. Neither of them are in slope-intercept form, so that means I've got a little bit of work to do. So what I think I'm going to do is I'm going to write the top one over here to the right. I like to have a little bit of space to work with. But I'm actually going to work with the bottom one here first because we want slope-intercept form. So Leanna, you already kind of hit exactly what we need to do. We need that y by itself. We need to solve for y. So getting that y by itself here, I'm going to first subtract 1x from both sides.
Do we have to put the 1 if we already know that it's there?
Technically, you don't have to. What you're going to see here, though, in a minute is because I'm looking for slope. I guess technically it's going to be
Yes,
1 over
for me, I
1.
always assume that it's nothing nice, there's always a 1 there.
That's fine. Whichever one you prefer, so long as you can still find the slope later.
Okay.
You don't have to put the 1 there. Sometimes, though, it ends up showing its face because we like to see that fraction eventually. So whenever works for you, do what works for you. So on the left, 1x minus 1x gone, leaves us with -1y equals -1x minus 3. Remember, don't get lazy on me, write that minus 1x on both sides, because otherwise you might accidentally combine things that you think are like terms, when in fact, I hope we all can agree that -3 and -1x are definitely not like terms. So just to kind of save yourself there. Then to get the y completely by itself, I'm going to divide everything by that -1 that's sitting in front of it. So the -1 divided by -1 on the left simplifies to +1. Leave me with y equals -1x divided by -1x is +1x. And -3 divided by -1 gives me a +3. So technically the bottom linear equation is now in slope-intercept form. And I would suggest, for the sake of consistency, let's go ahead and see this one all the way through. Let's get it on our graph. So what is the y-intercept? It's a +3. And our slope is 1. But if I'm thinking in terms of rise over run, I would write it as 1/1, running into my graph here. So if I was getting this on my coordinate plane, y-intercept starts us at +3. A slope of 1/1 has me traveling up, rising 1 unit up, running to the 1 unit to the right. And slopes of 1 really gives us a lot of points to see. Or vice versa, I could go down 1, left 1, which we don't know yet which of these points it's going to be intersecting at. Oh gosh. That gives us our first linear equation. All we have to do is repeat a similar process for the second. So same goal, we're really trying to get the y by itself. So I'll zoom back out here in just a moment. So on the second one here, I'm going to subtract 1x from both sides. Which leaves me with 4y equals -1x minus 8. And then I'm going to divide every term by +4. The 4 divided by 4 on the y simplifies to 1, which hides. And then this equals, watching our divisions carefully here, -1 does not divide nicely by 4, but that's okay. I like fractions for slopes. I'm going to get a -1/4 x. And then -8 divided by 4 gives me a -2. What's our y-intercept?
-2.
The -2. And our slope?
-1/4.
-1/4.
So the 4 is positive, right?
Right, so you're talking about on the slope?
Yeah.
So that negative sign, we can only use it once. So either you're going to treat the 1 as negative or the 4 as negative.
So
Never-
it has to be either or.
Either or, never both at the same time though, because a double negative
It's a positive.
is secretly a positive. So you can only use it once.
Okay.
So this one has us starting at -2 on the y-axis. And with a slope of -1/4, I'm going to rise, technically fall 1 unit because of the -1. and then run to the right 1, 2, 3, 4 units because of the positive 4. So that's what happens if you treat the 1 as the negative. If you kind of reverse it, a positive 1 would have me going up 1 unit, but if the 4 was negative, that's where I would travel to the left 4, which is important because that's actually where it's what we're looking for.
Where they intersect.
Mm-hmm. And for this one, where do they intersect? Ooh, close.
-4, -1.
-4, -1.
Is the x-axis.
X always comes first. Yep.
You ever had Dunkin' Donuts iced coffee?
I have not.
Shit tastes like whiskey. It is potent.
So I'll try to squeeze my problems in there.
Hey, Dust. And John.
So again, to summarize, if we're solving by graphing, we need them in slope-intercept form. We graph the lines. We find where they intersect. That point is our solution. So that's kind of the summary of that whole page there. Now, going to the next page, we're going to continue to solve our systems of equations, but now we're going to introduce our other two methods, next of which is substitution, which, if you'll see here, is then followed shortly by elimination. So for substitution, a little comment I think I'm going to throw in there for substitution. Aside from the fact that it is specifically asking us to use substitution, I know that substitution is a good option when one of the variables is already by itself. So anytime you hear substitution, we should think, I like one of the variables already by itself. Now you're in luck. This entire page for substitution,
There's one variable already. by
there's
itself.
always at least one variable already by itself. So I wasn't extremely mean. I actually kind of started the substitution process for you. And I've also specifically said use substitution. So these problems really strongly favor this method. So it cuts out some of the extra work that you'd have to do if you tried using one of the other methods. Now, good news is tomorrow for the test, I will give you kind of snippets from the notes, from substitution and from elimination as a reference sheet. I'll have that provided for you. I'll just need to remember for those of you who are online, I'll need to add that to my test document as well. But that way you kind of have that process that we covered in the notes. So you don't have to panic about, okay, which step comes next. It's more about, do I know how to follow these instructions? So for substitution, like I've already alluded to, I really, really, really like one of the variables by itself. And in this first example here, which variable's by itself?
Y.
The y, and which equation? The top one. So after one of the variables is by itself, which is technically the first part of the first step, the second part of the first step is to box in whatever that variable is equal to. So in this case, wherever now I see a y, I can replace it with 4x plus 24. Now, Miranda's saying we're put it into the negative y, and we want to be careful here because it's not equal to negative y, it's equal to positive y. So a trick that I would suggest here is it may be useful to write the -1 that's hiding there because I don't actually want to touch that -1. All I'm replacing is the y that's beside it. That -1 will actually stay there. But what happens then, so that first equation tells me anywhere you see a y, you can remove it and in its place put 4x plus 24.
So it's just a multi-step equation.
It's going to turn into a multi-step equation.
Okay.
Absolutely. So what's going to happen is in this process now, it's going to create kind of a hybrid equation where it takes the first equation, changes the second equation, but then it's something that we can then solve. So the bottom equation would then become negative 4x minus 1, but instead of times y, wrapped in parentheses, I'm going to drop in or substitute the 4x plus 24, and then that's all still set equal to 8. So the only thing that's really changed there is that y is gone, in its place 4x plus 24. But as Leanna was pointing out, all that really does for us is create a multi-step equation. So we go all the way back to, I think it was like day 2 of this term. We run through our list for solving equations. Step 1, what parentheses come first. So the negative 4x there at the beginning is going to stay put. Distributing the negative 1 times 4x is going to give me a negative 4x. And then negative 1 times 24 is going to give me a negative 24. And that's still set equal to 8. After parentheses, what do we check for next?
Like terms.
Like terms. They must be on the same side.
The negative 4 and the negative 4.
The negative 4x and the negative 4x, they're right there beside each other. Be careful though. Some of us are tempted to say, oh, they cancel out. Excuse me. But you're combining them, you're adding them. Negative 4 plus negative 4 is in fact negative 8x, which Miranda also has thrown in the chat for us as well. So I get negative 8x minus 24 equals 8. And now it's just a 2-step equation. Getting x by itself, I'm going to first add 24 to both sides. Which removes it from the left. Leave me with negative 8x. On the right, I'm going to get positive 32. And then last but not least, how would I finish solving this one? Divide by that negative 8 on both sides. So the good news is what I'm hearing is you guys know how to solve multi-step equations. What's going to be tricky is going to be this first substitution that you have to do to get the equation that you can then solve. Because here we're going to end up with x equaling negative 4. And I'll tell you what, once you find that first variable, it should get notably easier because you've got half the information. But what do I need for my final solution? I need the y that goes with it. Because remember, we're looking for a point of intersection. And all points are ordered pairs. Ordered pairs have both an x and a y. Now we're in luck. We already have an equation where the y is by itself. Our top equation tells me that y is just 4x plus 24. But what I now know that I didn't know moments ago is that the x is negative 4. So I can rewrite that equation to say that y equals 4 times negative 4 plus 24. 4 times negative 4 gives me negative 16. And negative 16 plus 24.
Negative 12.
Not quite. Positive 8. Good news is you can use calculators to walk you through some of these smaller steps. Don't mind me. OCD steps in, makes it pretty. Now remember though, you're not done until you have written your final solution as an ordered pair. And for this one, what do we have? Negative 4 positive 8. Now remember, regardless of which order you find them in, x always comes before y. So in terms of the flow of problems, I took the top equation, dropped it into the bottom equation, got a new equation, solved that new equation to get one of my variables, took that variable, dropped it into one of the equations, in this case the top one, and solved it again. So it's very, very, very systematic. No pun intended, being system of equations. It's a very repetitive process. All that changes are the signs and the values. So long though as you are taking the time to be organized, you should be okay. So let's try the next one. Do we have a variable by itself? Which one? The y in the top equation, and that y in that equation is going to be replaced with what? Or excuse me, what are we setting that y equal to?
+2, what? See,
That's where it's going, but the y on the top tells me that anywhere I see a y, we're going to replace it with negative 8x plus 3, that whole thing. Now the y in the second equation is where we're going to make that substitution. Everything else in that equation is not going to move. Everything else stays exactly where it's at. So that bottom equation is going to become 16x plus 2, but I'm going to remove the y and in its place put the negative 8x plus 3, close the parentheses, and that is still set equal to negative 1. So that is the bottom equation, but the y is now negative 8x plus 3, and that is thanks to the top equation, telling me that y is negative 8x plus 3. But then for our purposes, we go back to what our instincts are telling us, and we go into solving mode. And if I recall, this one's a trick, so I don't think I need to go that far. What should catch your eyes first?
Parentheses.
The parentheses. So the 16x is going to drop down. The 2 is going to distribute in. 2 times negative 8x is going to give me a negative 16x. 2 times 3 is going to give me a positive 6 is equal to negative 1. After parentheses, we check for like terms. So 16x and negative 16x combine to make 0. So in this case, something weird happens. These like terms, when combined, become 0, which for our purposes causes them to disappear. So that tells me that, my variables disappeared. This is a special case, which is the first step to realize. The second thing you need to do is figure out which one. And to do that, we need to look at what's left over. So Miranda's on the right track in the chat there. What is left over? Positive 6 set equal to negative 1. How would you describe that statement? Does 6 equal negative 1?
No.
No. So would you say that that's true or false? A false statement
No solution.
means that there is no solution. So even though that it's expecting an ordered pair there, couldn't just give it away, the surprise. I would actually instead, I'm just going to write the word no above the word solution and box that in instead. As soon as the variable disappears, you have to adapt. You have to think, okay, there's nothing I can actually solve for. I need to sit back, look at what's left over, and determine whether it is true or whether it is false. False statements mean no solution. True statements mean how many? What? Many, or specifically infinitely many solutions. Because otherwise, if it's solvable, you'll actually be able to go through the process like we did on the first one. So I know we started a little bit late. I'd like to knock out this page before we head to a break. So we got 2 more problems and then we'll take a short break, come back, knock out the second half of this test or this review. Third one here, I like to throw this one in here because it throws people off. Any ideas why?
Because they're both, why
Because
is
they're
wrong.
both in slope-intercept form.
They're both in slope-intercept form. Lena said both the y's are by themselves. So at this point, some students are really, really tempted. They want to graph. But what have I not provided you?
Graphing.
I haven't provided you the coordinate plane for the graphing. I've asked you to use substitution. So what really throws people off is, well, now I have 2 variables by themselves. Which one do I box in? Doesn't actually matter. I just need, if you remember, I just need one of the y values, or excuse me, one of the variables to be by itself. So we have a question here. We don't have an x coordinate yet. So we don't actually have anything yet. We don't have the x or the y, but that's okay because the first step of substitution says that if a variable is by itself, or you get it by itself, you box it in. So because the top variable or the top equation is the first one I can see, I'm going to box that in and say that anywhere else I see a y, I'm going to replace it with 5x minus 17. Now, quick throwback to the one above it. Our y for this one was in the mix. It was thrown in the middle of the problem. There was things we had to work out. This system, the y happens to also be by itself. That's okay. Doesn't matter where it's at, because wherever it is, I'm going to replace it with the 5x minus 17. So Miranda's saying, wouldn't it be 5x minus 17 equals 7x minus 23? That's exactly what it becomes. So the 5x minus 17 replaces the y on the left of the bottom equation. But then the bottom equation on the right stays the 7x minus 23. And although it's a little bit different, it doesn't have parentheses like the last one. That's okay. We can still solve it by following our steps. So if there's no parentheses, what do we check for next? Like terms.
And there is none.
There aren't any because they're not on the same side. So the third thing we look for is if the variable's on both sides, which in this case it is. Which one do I usually suggest moving?
The lower one.
The smaller one, which in this case is that 5x. So I'm going to subtract 5x from both sides. So 5x, take away 5x on the left is gone, leaving me with negative 17. On the right, 7x, take away 5x, leaves me with 2x. And the minus 23 falls down. All that's left now is to get that variable by itself. It happened to land on the right-hand side. That's okay. We're just going to start moving everything else off of the right. Starting with what?
Add the 23.
We're going to add the 23. I don't think it froze. Nope, we're still going good. So negative 17 plus 23, I believe, gives us a positive 6 equals 2x. The negative 23 plus 23 is gone. And then last but not least,
Divide by the 2.
divide both sides by the 2.
I wrote mine different. I got the same answer.
You should. Did you move the 7x instead?
Yeah.
Because you like everything to the left?
Yes.
That's okay. And it should give you the same answer because I got 3 equals x. So I end up having to flip it back around to say x equals 3. Yours probably already landed on the left-hand side. So your steps, still the same process. You're perfectly fine. Am I done?
No, you gotta find why.
I have to find the y that goes with it. So technically, because both of the y's are already by themselves, I easily could use either. But for the sake of consistency, I'm just going to go ahead and use the one that I boxed in. So the y equals 5x minus 17. I now know that x is a positive 3. So I can rewrite this as y equals 5 times 3 minus 17. I think I made it too long. I get y equals 15 minus 17, and 15 minus 17 gives me a negative 2. I did.
So I solved for the bottom one, and I still got the 20.
You should, absolutely. So Leanna, for those of you who didn't catch what she said, Leanna said she actually used the bottom equation to replace the x with 3, but got the same conclusion. And Miranda's clarifying there, we got to plug that 3 in wherever x is. So it doesn't actually matter which of the original equations we use. They both should result in the same solution. Because if you think about it, we're looking for the point that they both share. So it doesn't matter which line you're traveling on. They both should end up crossing at the same point. And that point in this case is 3, negative 2. One more here before we take a short break. This one's a little bit different because we have a system that's already set up kind of favoring substitution, but this time it's not even necessarily asking for the entire solution. It's asking for just the value of y. So as soon as I find y, I'm done. Be careful though, don't accidentally write down the answer that is the x, because it's also there in the options as well. But so long as we go about it the same process we've been going through, we should still be okay. This time, the variable that's by itself is in the bottom, and it's the y again. So I'm going to box that in. And wherever I see a y, I'm going to replace it with the 5x minus 14. And the only other y I see is right here above it. So the top equation is going to become 7x minus 3, but instead of y, I'm going to put 5x minus 14 equal to 10. How are we going to solve that first? Parentheses first. So we're going to distribute. 7x falls down. Negative 3 times 5x gives me a negative 15x. Negative 3 times negative 14 gives me a positive 42. Is equal to 10. After parentheses comes combine like terms. In this case, we got the 7x and the negative 15x, which gives us a negative 8x plus 42 equals 10. And then we're just trying to get that variable by itself. Yep, subtract 42 from both sides. So negative 8x equals negative 32. And then divide both sides by that negative 8. You get a positive 4, which I believe is an option down below, right?
Yes. But it says solve for y, so we have to plug the x and
Oh, goodness. Sorry. My tool. One of these.
solve it.
So be careful. So you guys, I don't know if you guys picked it up on the mic here, but yes, 4 is one of the options down below, but Leanna pointed out that we're looking for y. So yes, we found x, that's great. It's going to help us find our y, but don't jump the gun and say, oh, my answer is B. Make sure you know what you're looking for. And in this case, we need to use that x is 4 and bring it back and let it help us find the y that goes with it. So for our purposes, I'm going to rewrite the bottom equation to say that y equals 5 times 4 minus 14. 5 times 4 gives me 20. And 20 minus 14 gives me 6. So the value for y is positive 6, which is option A. So make sure you're reading the directions carefully. There's 2 problems like this on the test tomorrow. All right, so our next page here, still solving systems of equations, but this time we're using our third method, elimination. Now for elimination, we like 2 things to be true before we can proceed in using elimination. First thing, we like everything lined up. What you'll notice on the examples I've provided, aside from the fact that the text is slightly askew, everything for the most part is already lined up for us. So that's good. Second thing we like, this one is a must. We need exact opposite coefficients on one pair of variables.
I know. I don't want to hear either. Hey, Josh, can I perhaps borrow a computer charger?
Do you remember which kind?
It was a small, fine one because Austin, my boyfriend, lost.
So somebody took a video, is our video?
All right. So we like everything lined up. We need exact opposite coefficients on one pair of variables. If we don't have that, multiplication is our tool to adjust as needed. So on the first one here, we're actually in luck because 1, everything's lined up. And interestingly enough, the coefficients on the x's are exact opposite. So are the y's, and so are the constants. So this is actually something unique that's going to happen sometimes. That when I go to add these 2 equations together, the x terms are going to eliminate. So are the y terms, which leaves me with what on the left-hand side?
Negative 30.
On the left.
Negative 30 and 30.
No, on the left,
Nothing.
everything cancel out. Nothing, which would be 0. And on the right, 30
They
plus,
cancel out too, if you turn the 2.
which gives me
0 equals 0.
0 equals 0. Do I have any variables left to solve for?
No.
No. So I say, well, I can't solve this one, but I can look to determine something about the solutions. How would you describe this statement?
It's true.
It is true. Which means what? So it wouldn't be undefined. Miranda has in the chat here,
Infinite
because
many solutions.
earlier we had that a false statement gave us no solution.
There's an infinite solution?
A true statement gives us infinite solutions. So I'll put infinitely many. So that is actually, we've now covered every possible case. If there is a solution, we're going to find it. We're going to find the X, we're going to find the Y, we're going to write our ordered pair. But in that process, whether it's substitution or elimination, if all the variables disappear, you can't solve it like you did anymore. You're done. You have to adjust. You have to look at what's left over. If what is left produces a true statement like this one did, you have infinitely many solutions. If it produces a false statement like the one earlier on the previous page, that means that there are no solutions. These are special cases. I think I only have 2 thrown in on the test for tomorrow, but be aware of them. There are 3 possible outcomes. Exactly 1 solution, which is our ordered pair. No solution, which is usually from a false statement, and infinitely many solutions, which comes from a true statement. So that one was a special case, not terribly typical of an elimination problem, but it does happen. Let's see one that's a little bit more common. So right off the bat, hopefully we see that for the most part, everything's lined up. The X terms above each other, the Y terms, the equal signs, the constants. It may also help to see the one that's hiding next to this Y. But what's the problem? What do I not have?
Like terms,
I don't need blank terms per se.
the exact opposites. No, you do.
Exact
No,
opposite?
not exact. The 6y and the 1y.
So the negative 6y and the 1y, they are opposite signs, but not exactly opposite. But also, I mean, I could argue that the negative 2's are really close. I would just rather one of them be positive. Can you think of a number we could multiply by that would change only the sign?
Negative itself.
You want the negative of it because a double
No,
negative.
-1.
Go ahead. Yeah.
It's a -1.
If you multiply a negative value by a -1, all it changes is its sign. So if I decided I wanted to eliminate my x's here, and I say, well, to do that, I need one of them, we'll say the bottom. If I wanted the sign to change so it became positive, I could multiply this entire bottom equation by nothing more than just a -1. Now, everything's going to change, but the change we're excited about is that this -2 times this -1 is going to become a positive 2x, which is going to give me that exact opposite coefficient. So what I like to do when I'm working these problems, I like to write my changed system off to the side here. I'm not touching the top. So -2x plus 1y equals 16. And the bottom, all that I'm multiplying by is a -1. So all that's really going to happen is all those signs are going to change. So -1 times -2x is going to give me a positive 2x. -1 times -6y is going to give me a positive 6y. And -1 times -12 is going to give me a positive 12. And why am I excited now?
How you can solve it.
What do you mean by solve it? What's going to happen?
The x is going to disappear.
The x's are going to disappear. They're going to eliminate each other, which is going to leave me with a one-step equation with one variable. So the -2x plus 2x is going to become 0, which drops away, which is good. The 1y plus 6y is going to give me a 7y. And on the right, 16 plus 12 is going to give me
28.
28. And what I'm left with is a one-step equation for which I could solve by doing what?
Dividing
Dividing by
the 28 by the 7.
the 7. So I get y equals a positive 4. Now, am I done?
No.
Not quite. Still got to find the other value, the x in this case. Does it matter which of the original equations I use?
No.
Technically not. Does anyone have a preference?
Easier one.
Well, easier is relative to each individual person.
The top one.
The top one looks easier to you? Okay. So I will copy down the top one here real quick. Negative 2x plus 1y equals 16. We now know that when we get to the y, we can replace it with a 4, which will change that equation to negative 2x plus 1 times 4 equals 16.
I have solved problems.
We're on number 2, solving systems by elimination. So on the left, parentheses hopefully catch your eye first. So that 1 times 4 is going to give me a 4. So negative 2x plus 4. And then we just have a two-step equation where we're trying to get x by itself. So first thing I'm going to do is subtract 4 from both sides. Leaves me with negative 2x equals 12. And then last but not least, divide both sides by negative 2. To get x equals what?
X equals negative 6.
X equals negative 6.
What's one?
Number 2.
What's one?
Yes.
Not yet.
No, not yet.
It's okay.
So what's my final solution?
Being 6 and 4.
Negative 6 and 4. So even though we found the y first, the x coordinate always comes first in our final solution. So our final solution is negative 6, 4.
So the first one is no solution.
The first one was infinitely many solutions, because when we eliminated everything, we were left with 0 equals 0, which was a true statement. True statements mean infinitely many. False statements mean no solution. So that second one there was relatively laid back as well. We got away with changing just very, very little. In fact, we really just made the sign change by multiplying by negative 1. Sometimes we have to change it a little bit more. So that's where our third system comes in. Everything's already lined up. But do I have exact opposite coefficients? No. So I see a 9 and 5 on the x's, a negative 4 and an 8 on the y's. Which one is screaming out to you? The x's or the y's?
The y.
What about the y's?
Because if you times the negative 4 by whatever number,
Mhm.
not negative, you can turn it into a positive 8y.
Well, I don't want it to be a positive 8y because we already have a positive 8y.
Negative times it by a negative, or a positive number.
Okay. So my question is why the y's? So I'm seeing Miranda's also suggesting they both multiply into 12. Which one? Are we talking about the y's? So not quite. They technically multiply into something a little bit larger. They could go into 24, but 8 doesn't go into 12 nicely. So close, but I could actually get by even shorter because let me ask you this. Does 4 go into 8 nicely?
Yeah, they divide into, like, they.
No,
do,
because one's negative.
But don't worry about the negative. How many times does 4 go into 8? 2. 2 times? Guess what I'm going to times by? By positive 2. 4 goes into 8 exactly 2 times. So if I multiply this entire top equation by a positive 2, that negative 4 times 2 is going to give me a negative 8. And I don't need to mess with the sign. They are already opposites. That's why I'm not using a negative value here. And I can get away with only changing the top one. Now, again, that doesn't always happen, but when it does, it saves you a little bit of work, or at least a little bit of multiplication. Because now my top equation, multiplying the 2 all the way through, is going to give me an 18x minus 8y equals 10. I got away with not changing the bottom one, so that one stays 5x plus 8y equals 13. When I add them together, the 18x plus the 5x is going to give me 23x. The negative 8y plus 8y eliminates. Bring down my equal sign. 10 plus 13 gives me 23. And what I'm left with, yet again, is a one-step equation. And to solve it, all I have to do is divide both sides by 23. Not 0. We're dividing, not subtracting. We should get x equals 1. Again, once you find the first value, it's going to help you very quickly find the remaining value, the remaining variable. So in this case, I'm looking for y. Do you guys have a preference which of the original 2 equations we use?
No.
No preference?
I just say 5x plus 8. So
The 5x plus 8y equals 13 works just as good as any. So we're going to use the 5x plus 8y equals 13. But now that we know that x is going to be replaced with a 1, we can write that as 5 times 1 plus 8y equals 13. Going through and solving, the 5 times 1 is going to give us a 5 plus 8y equals 13. And then to get the y by itself, I'm going to subtract 5 from both sides. Gives me 8y is equal to 8. And then to finish it, I'm going to divide both sides by 8. And get y equals 1. Now, be careful. This is a coincidence. They don't always turn out to be the same number. It just happens sometimes. What's our final solution then? 1, 1. That is the point where those 2 lines intersect if I were to go back and graph them, which thank goodness we're not. Last one here on elimination, a little bit trickier because we're not going to be able to get away with changing just one of them, and I'll explain why here in just a moment. But before we do that, let's first notice that we're not actually looking for the entire ordered pair. We are only searching for the value of x. And I'll tell you why I would make some suggestions there, because if I can cut out some steps, all the better. So for this one, it is already lined up. But what I mean by we can't get away with changing just one of them, if you look at it, does 6 go into 8 nicely? It does not. You can't think of anything to multiply 6 by to turn it into an 8, and vice versa. You couldn't turn an 8 into a 6 easily with multiplication. Same for the 2 and 9. 2 doesn't go into 9 nicely. 9 certainly doesn't go into 2 nicely. So we're a bit stuck in the sense that we can't change one into the other. However, we could change both into something new altogether. So this is where knowing your multiples comes in handy, because if you know what you can eliminate, all the better. But I'm going to push it one step further and remind you what we're looking for, which in this case is what? We're looking for x. So would it make sense for us to try to eliminate the x's?
No.
If I eliminated them,
Why?
if I eliminated the x's, I would first end up finding the y, which is okay. That y would help me find the x, but it would double my workload. If I could come up with a way to eliminate my y's, what I'd be left with very quickly is what my x is. So that's my goal for you. Let's look at the y's. I want them to eliminate. Now we've already discussed that 2 doesn't go into 9, 9 doesn't go into 2, and they both happen to be negative, so we have some changes to do. But first, Miranda's already ahead of me. Miranda's saying 18. Why is she saying 18?
Because she's multiplying 2 and 9, and 2 negatives equal positive.
Well, close, yes. We'll worry about the signs in just a moment. But they both divide, well, technically, they both multiply into 18. So 2 times 9 becomes 18, 9 times 2 becomes 18. And I want them to be exact opposites, so if I can get them to be at least the same value, we're on track. So let's first focus with the top equation. Our goal is an 18 on the y's. What would you multiply the 2 by to get it into an 18?
9.
Times 9. So we'll worry about the sign here in just a moment. So Miranda's suggesting -9, and she's not technically wrong. If she wanted the top one to be positive, that would work. But we have a couple options here. I'm going to go with the positive 9 just because that's the first thing I heard. So the top equation, multiplying through the 9, I'm going to get 72x minus 18y equals 18. Now, I need that -9y to become what?
Positive.
I do need it to become positive, and not only positive, but it
You
needs
needed it to become 18.
it needs to become 18 as well. So -9 times what becomes a positive 18? Close. -2. So the -2 is going to have two effects. It's going to change the 9 into an 18. It's going to change the negative into a positive. So what I end up with is -12x plus 18y equals a positive 42. And I'm excited because as I go through and add these two equations together, 72x plus a -12x, I believe gives me 60x. The -18y plus 18y is gone. 18 plus 42 gives me 60. And what I'm left with is just a one-step equation, for which I just have to divide both sides by 60. And I get what for x?
X equals 1.
X equals 1. So then what do I do with that x?
You plug that in for,
No, because you really don't have to technically solve for y. You can either find the value of x.
Good catch. So I tricked you a little bit. I kind of set you up. If I was looking for the entire ordered pair, I would plug that 1 back into one of the x's, solve for y, celebrate with an ordered pair. But this one was a little bit unique in that it was only asking for the value of x, which we just found. So our value of x is 1, which is option C. Now, the tricky part is telling students that this wasn't the only way to solve it. This may have been the most efficient way, but it's not the only way. So you may take a slightly different route, and it doesn't mean that you're wrong. If you're worried about being wrong, let me know. Walk me through your process. We'll talk about it, and we can go from there. But it's not practical to cover every single route together because we would be here all day on just one problem. So that is elimination. So we've covered all 3 methods for systems of equations. We had graphing, in which we needed to see where they intersected. We had substitution, in which we really liked one of the variables to already be by itself. And we had elimination, where we preferred it to be lined up, and we also needed opposite coefficients. So those are the 3 methods we covered in this short unit. But there are a few other things that we did squeeze in as well. And the next page is how we handle a system of inequalities. So first off, systems of inequalities, I'm going to squeeze in here up in the top margin the symbols that we use because they told us 2 different things. Again, this is information you will have provided to you on the test tomorrow. But the inequality sign tells us 2 pieces of information that we'll need. So a less than symbol will tell us that we need to use a dashed line, and we will shade below that line. A greater than symbol also tells us to use a dashed line, but to shade above it. A less than or equal to sign gives us a solid line for which we'll shade below. And a greater than or equal to sign gives us a solid line for which we shade above. Oh, darn it. So that'll be key information to help us graph these to see our final set of solutions. Because remember, we're really just looking at which range we shade twice. Which shaded area do both of our inequalities share? And again, I'll have a small table with this same information provided to you for the test because I'm less interested in whether or not you can memorize it. I'm more interested in whether or not you can use this information to graph them successfully. Now, why am I excited about this first set of linear inequalities?
Because it's in slope-intercept form.
They're both in slope-intercept form, which means straight away we can begin to pull the information we need to get this on our graph. So I'm going to first split my little area here so we can start identifying the information we need one at a time. So I'm going to start with the top one, already in slope-intercept form. So we should be able to pull everything we need, starting with the y-intercept, which is the -1. Follow that up with the slope, which is a positive 1/1. I like that you already converted that into a fraction. That'll help us with the rise over run. Then I look at the symbol, which is a greater than or equal to symbol, which tells me 2 things. What type of line?
Solid.
A solid line. And with respect to that solid line, yep, exactly, Leanna, we shade above. That is everything we need to graph the top inequality. So before I try to juggle too many things at once, I'm going to get all that on the graph before I try to tackle the second inequality. So this one starts at -1 on our y-axis. From there, it's going to go up 1, right 1 due to the slope. Or if I prefer, down 1, left 1, just to see all the points I can fit on there. And then according to the inequality symbol, this line should be solid. And with respect to this line, again, remember, we're going to have two things to shade. So ever so lightly, just to serve as a reminder, I'm going to just kind of very lightly shade above that line, just so I remember where I was focused for the first one. So we have half of the information on our coordinate plane to start us off. Then I transition into the second one. So make sure you're not accidentally jumbling your information together. I would say, like we did here, see it all the way through to the end before adjusting to the second one. The second one, however, though, is also in slope-intercept form, which is nice because then we just start listing the information similar to the first, starting with the y-intercept, which is a +2. The slope is a -1/2. And notice that the computer likes to put the negative sign next to the fraction. I recommend putting it on top. That'll help you with your rise over run. Then we look at the inequality symbol, which is a greater than symbol, which is going to tell me that my line needs to be dashed, but I will still shade above as well. So the y-intercept has us starting at +2. With a slope of -1/2, we're going to go down 1 unit to the right 2 units, which we can do twice. Or we can go up 1 unit to the left 2 units, which we can also do twice to give us a total of 5 points.
Can you zoom in a little bit?
Mm-hmm. Yeah, no problem. The inequality sign told me that this line should be dashed. And it also told me with respect to this line, we needed to shade above as well, which is just that small region there up kind of towards the top right of the coordinate plane. But we're not done yet. We've got all the information on the coordinate plane, but what we're ultimately interested in is not all the shaded regions that we shaded at least once. We're really only interested in the one section that we shaded twice, which is going to be right here, kind of this top middle section of our graph. Make sure, though, you don't cross our lines that we put in, because we need our region to be above not only the solid line, but also above the dashed line. Now, if you're picky like me, I usually go back and erase the extra just so I can see where my final graph region is located. But what you should end up with is this section right here. What's a bummer about the second one? Not in slope intercept form, so we have a little bit of work to handle up front. So let me set up my workspace over here. Top one, I'm going to write down first. 1x minus 1y less than or equal to 1.
Is the top part shading? Is the top part shading?
On the first one?
Yeah.
Top little section up there.
Okay.
Second linear inequality, we're right here off to the right. 1x plus 1y is greater than or equal to -3. And then we dive right into it, trying to get the variables or the y by itself in each. So first one here, I'm going to subtract 1x from both sides. Which leaves me with -1y is less than or equal to -1x plus 1. And then I'm going to go through and I'm going to divide every piece, both sides, by the -1. Does anyone remember what happens when you divide or multiply both sides by a negative value?
They turn the opposite.
Well, the signs will turn positive. The negatives will become positive, but all the signs actually become
They're
opposite.
opposite.
But that includes the inequality sign.
It flips.
It flips. So we end up getting y is now greater than or equal to a positive 1x minus 1. Haven't given myself much space here. That's my bad. We'll make it work. So the y-intercept is what?
-1.
-1. The slope
1/1.
is 1/1. And with a greater than or equal to symbol, that's going to tell me two things.
It's a solid line.
Solid line and
Shade above.
shade above. So I squeezed it in there, but like I said, we'll make this work. But while I have it there, I'm going to go ahead and get it on my coordinate plane, starting with the y-intercept at -1, put our first point. With a slope of 1/1, we're going to go up 1, right 1, which we can do several times. Or alternatively, down 1, left 1. Drawing a solid line. And ever so lightly shade above that line. So we still have a second one to come back and address.
Now, if the shading gets too overwhelming, do we have to shade then, or can we just wait?
If you want to wait till the end to shade, that's okay. I've had some students do that. So long as you recognize you're cutting your graph into 4 sections, you want to find the one section that meets both inequalities.
Okay.
So I'm okay with that. Absolutely. So coming up to our second inequality here, a little bit of work to do up front as well, getting that y by itself. So first thing I'm going to do is subtract 1x from both sides. Leaves me with 1y is greater than or equal to -1x minus 3. Then I'm going to divide everything by 1, which really doesn't change much, does it?
Not really.
it can make me feel better about hiding the 1 next to the y on the left-hand side, but the inequality sign stays the same. Negative 1x doesn't change, negative 3 doesn't change. But now at least it looks more like slope-intercept form, so I can start identifying the pieces that I need. Starting with the y-intercept, which is
-3,
a -3, followed by the slope,
-1/1.
which is a -1/1. Then looking at the inequality symbol, which is a greater than or equal to symbol,
Shade above.
solid line, shade above. So with that information jotted down to the side there, we're going to find -3 for our y-intercept with a slope of -1/1. We're going to go down 1 unit, right 1 unit, or up 1 unit, left 1 unit, which is going to give us even more points. This line is also solid. And we also want to shade above it. But remember, we're really mostly interested in where we shaded twice. So for our purposes here, it's going to be this region in the top section of our graph. If you got rid of the extra, this is going to be the region that you're looking at. So with a little bit of added effort up front, getting those inequalities in slope-intercept form, just like with the first, we're able to get them on our graph, get our shaded regions in there, and be good to go. So last one on this page, a little bit different setup. We actually have a multiple choice question where we have 4 different graphs already provided for us. What we need to do so that we make sure we make the correct selection is it would really help if we had the information jotted down for these 2 inequalities, because then we can make some better comparisons. And unfortunately, right now, neither of these inequalities are in slope-intercept form, which means we have a bit of work to do up front. So I'm going to start with the top one. 1x minus 3y is less than 6. So getting that y by itself, I'm going to first subtract 1x from both sides. Which leaves me with -3y on the left is less than -1x plus 6. And then I need to get the y by itself by then dividing everything by -3. Now, a couple things are going to happen here. First off, y is by itself, but I did divide by a negative, so the less than symbol becomes a greater than symbol. The -1x divided by -3 is going to give me a positive 1/3 x. And 6 divided by -3 is going to give me a -2. So for this first inequality, we now know the 4 following bits of information. The y-intercept is -2. the slope is 1/3. And according to the inequality symbol, it's going to be a dashed line for which we will shade above. Now, again, we don't actually have to graph this, but it may be worth taking a quick peek here, and right off the bat, guess which one I can eliminate? Well, actually, maybe not.
They're all dashed.
Well, they are all dashed, but if I look here, B does not cross the y-axis at -2. So B would be off the table.
Either does A, it looks like.
A doesn't look like it goes through -2 as well. And if I actually look one step further, my inequality symbol here on the second one is going to tell me that the second one has to be a solid line. So I would argue that A could probably be eliminated as well. So good news, if I have to guess, I now went from a 25% chance of guessing right to a 50% chance of guessing right. But it's not going to be until I take a look at the second one to make my final decision. So 5x minus 3y is greater than or equal to -6. If I can get that y by itself, I can list the 4 pieces of information for that one to make my final decision. So first subtract 5x from both sides. Leaves me with -3y is greater than or equal to -5x minus 6. And then divide every single term on both sides by a -3. Now, because I divided by a negative, my inequality sign here is also going to flip. Greater than or equal to becomes less than or equal to. -5x divided by -3 is going to give me a positive 5/3 x. And -6 divided by -3 is going to give me a positive 2. Running into my answers here. Whoopsies. From that, though, I now know that the y-intercept for the solid line is going to be at positive 2. The slope of the solid line is going to be a positive 5/3. And the inequality sign, of course, tells me that it's going to be solid, but it also tells me I need to shade below the solid line. So wherever the final shaded region has to be, it has to be above a dashed line, but below a solid line. Well, there's only one that matches. A is already off the table because they're both dashed lines.
I can't see the graphs, so
You can see them on yours though, right?
a little bit, but it's still, I think D is the answer.
D is the correct answer because D, if you went through and fact checked every bit of information, the y-intercepts match up for each line, the slopes match up for each line, but most importantly, this shaded region is below the solid line, but above the dashed line. Finally, moving on to our last page of the review. Thank you guys for sticking with me. Real quick, just because it might be worth mentioning earlier rather than later, this first problem has multiple parts. We're going to have to write our system first, solve it, and then explain which method we used. I think it's worth like 5 points. The second one is going to be worth bonus points tomorrow. So for the sake of the video, I'm going to go through this entire page. You're welcome to stick with me in person now if you'd like. But know that I will solve the rest of this page, but number 2 on the last page of the test will be worth extra credit. So it's not required. It is a little bit more challenging, but it's worth throwing that information out there real quick. But number 1 will be required. and it's worth the most points on this page. So first thing we need to do is to write a system of equations to allow us to then solve and find the answers. But up here in the instructions, very boldly, very loudly, it's saying define your variables first. Now, normally that would be having to jot down somewhere in the margin which variable represents what. But what I like to do is if I already know what the answers that I'm looking for are representing, I like to throw my variable next to them. So I'm going to say that my X is going to represent the cost per senior ticket, and that my Y is going to represent my cost per student ticket, just so I don't have to try to retrace my steps later when I find the X and Y. But with that information now identified, as I read through this, I need to be thinking about two separate equations that I can write. So it says that the school that Andrea goes to is selling tickets to a spring musical. On the first day of ticket sales, the school sold 6 senior citizen tickets and 13 student tickets for a total of $199. The school then took in $242 on the second day by selling 12 senior citizen tickets and 14 student tickets. Find the price of a senior citizen ticket and the price of a student ticket, which those are my variables that we've already identified. So what I would do if I was working through this problem is I would write an equation for each of the days, because that's the only way I can write two equations that use both variables. So the first day says that they sold 6 senior citizen tickets and 13 student tickets for a total of $199. So that's going to give me 6x plus 13y equals $199. The second day then says that they made $242 selling 12 senior citizen tickets and 14 student tickets. So that would give me 12x plus 14y equals 242. So the top equation takes all the information for day 1, the bottom equation, all the information for day 2. There's most of the points right there. But what I need to do now is to solve. Which method do you think would work better here? Graphing, substitution, or elimination?
Elimination?
I would agree with elimination because everything's already lined up. All we need to do is get one of the variables to have opposite coefficients. And if you're looking carefully, if you look at the x's, I noticed that 6 goes into 12 exactly 2 times. I do need the sign to change also, however, so I'm going to multiply that entire top equation by -2, which is going to change the top equation into -12x minus 26y equals a negative, I want to say that's 398. If you want to check that for me, Leanna.
Yep, you're right.
Good. I'm not going to mess with the bottom equation because I already have a positive 12x there for me. So plus 14y equals 242. And then I'm ready to add these two equations together. Because now in adding these two equations, my x's are going to eliminate. -26y plus 14y is going to give me a -12y. And -398 plus 242 is going to give me a -156, I believe. And then to finish solving this one, all I have to do is divide both sides by -12. Y equals 13? Awesome. Positive 13. And because we've already identified our variables, I already know what Y represents. And in this case, that is the cost per student ticket. So I can put 13 on that line. But what do I still need? I need the x. And if I was solving this one, I would probably go with the top equation just because those values are a little bit smaller. But again, either equation would work. So the top equation was 6x plus 13y equals 199. I now know that y is 13. So this becomes 6x plus 13 times 13 equals 199. Thirteen times 13 gives me 169. And then to solve, I'll first subtract 169 from both sides. This gives me 6x equals 30, I believe. And then divide both sides by 6. And I get x equals 5.
I did the bottom one just to be funny.
And did you still get the same answer? Perfect. So Leanna used the same, or the bottom equation instead, but still came out with the same solution, which should happen. But what we find out is that each senior's ticket is going to cost $5. Each student ticket costs $13, which makes a bit more sense because typically there's a senior citizen discount. Now, which method did we use?
Elimination,
And do you remember why we chose elimination?
because they were both lined up.
Because they were all lined up. So elimination because everything was lined up. Good. So if you'd like to cut out there, knowing that the last one is worth extra credit, that's fine. But like I said earlier, for the sake of the video, I'm going to go ahead and do the last problem for anyone who's interested. I am, however, going to go through it a little bit faster, just again, because it's meant to be challenging. So there should still hopefully be some sort of challenge to it. So the last one says that Matt only has quarters and nickels in his car. He has 20 coins that value $2.40. How many quarters and nickels does he have in his car? Well, right off the bat, my variables is going to be the number of quarters will be my x. The number of nickels will be my y. What's challenging about this problem, though, is how little information it seems to give us. So what I need to do, though, is look at the information given, and I notice that the only two values were provided are measuring two different things. The 20 is talking about how many coins. The $2.40 is telling us how much those coins are valued at. So really, I have two equations. One's going to be quantity. One is going to be value. Well, quantity is easy. If I take all the quarters plus all the nickels, there's a total of 20 coins. All the quarters plus all the nickels equals 20 coins. The second one takes a little bit of thinking because now I need to think about the value. How much is a quarter worth? So 25 cents per quarter plus 5 cents per nickel. And here's where I lose students a little bit. If 25 and 5 are measuring cents, I need to convert the $2.40 into just cents, which for my purposes will be 240 cents. If you think,
just remove the decimal.
pretty much in this case, you remove the decimal because it would take 240 pennies to make $2.40. Now, this one can go a couple different routes here. For the sake of variety, I think I would solve this one with substitution personally.
Well, it would be easier.
So I would take the top equation, x plus y equals 20. And I would solve for, it doesn't really matter. I'm going to solve for y and subtract x from both sides. So y is now by itself, and it is set equal to 20 minus x. And substitution says once you have a variable by itself, you can box in what that variable is set equal to. So in this case, anywhere else I see a y, I can replace it with 20 minus x. Well, I have a y in the second equation I wrote, which allows me to rewrite it as 25x plus 5 times 20 minus x equals 240. And then I go down the journey of solving this equation, following the process I've used before. So parentheses first, whoops, distributing of 5. This is going to become 25x plus 100 minus 5x equals 240. Combine like terms, 25x and negative 5x will give me 20x plus 100 equals 240. And then to get x by itself, I'm going to subtract 100 from both sides. That gives me 20x is equal to 140. And then, what a long process here, I divide both sides by 20. So x equals 7. Whoops. Remember, x represented my number of quarters. So there are 7 quarters in his car. We still need to know how many nickels. Well, it just so happens that if I know what x is, I can come back here to this box I used earlier and say that y just equals 20 minus x, and x in this case is 7. 20 minus 7 gives me 13. What a process. Remember, that one is worth extra credit just because of how you kind of have to read between the lines to get the information you need.
Can you put up number 4?